Good. So welcome to today's seminar with Jeremias Berg from University of Helsinki on MaxSat solving. So this is an area that has seen quite exciting developments in the last few years, which Jeremias will tell us about. In fact, about some of the very latest, hottest news, which I think was even the best paper at the SAT conference last year. And Jeremias also got an award for his PhD thesis. So very, very excited to have you here, Jeremias. And please, the floor is yours.
Thanks very much. I'm very happy to be here. So, as Jakob mentioned, I'm going to be talking about MaxSat solving, and more specifically, implicit hitting set-based MaxSat solving, and even more specifically about abstract cores in implicit hitting set MaxSat solving. And this is joint work with Professor Fahim Bakkus, and the slides are also based on material from Matti Järvisalo and Ruben Martins. And then I need to click here to be able to change the slides like that. So first, very quickly about myself. I'm a postdoctoral researcher at the University of Helsinki, working in Matti Järvisalo's group. I defended my PhD thesis on MaxSat and applications of MaxSat a few years ago. Afterwards, I went on a few visits, one to Melbourne to visit Peter Stuckey, and one to Toronto to visit Fahim Bakkus, where this work was also done. And at the moment, I'm working mostly on these declarative methods for solving NP-hard optimization problems. So in a way, branching out from MaxSat as well. And as Jakob also said, feel free to interrupt me at any point. If you don't have any questions, I'm assuming we'll be closer to 1 hour than 2. But if you have lots of them, I'm happy to also go about 2 hours. So first, some general words about maximum satisfiability, or MaxSat. MaxSat is an exact Boolean optimization paradigm, and we make use of the extraordinary success of Boolean satisfiability, SAT solvers. And in recent years, there's been a lot of developments in solver technology. I'll show you a few graphs later on. And as a consequence, or because of that, there also are more and more interesting real-world applications of MaxSat. And we've seen that in many of these applications, MaxSat solvers actually offer an alternative to many other paradigms, such as, for example, integer programming. And we can get these provably optimal solutions, and nowadays also good approximative solutions. And the fact that we're working with propositional logic means that MaxSat is especially good for these kinds of, this is a bit hazy as a term, but the kinds of problems where the underlying structure is somehow Boolean, and you've got lots of logical constraints that you need to satisfy. And then the thing I'm going to be focusing mostly about, so-called implicit hitting set-based maximum satisfiability. And in a very short way of saying, well, defining that is a solution approach where you decouple MaxSat solving into a separate reasoning step, which is a core extraction step, which is done by a SAT solver, and then an optimization step, which is sort of finding a minimum cost solution candidate, and this is done by an IP solver. And why you would like to do this is that then you avoid sort of increasing the complexity of your SAT solver calls. You sort of hand off some of the numeric reasoning to an IP solver instead. And this is very effective. And implicit hitting set IHS-based solver has been in the top positions in the evaluations since 2015. And sort of beyond MaxSat and even beyond NP, the same framework has been instantiated in various different applications in general, and can be thought of in quite generally in different problems. And here's sort of the outline for my talk. I'll speak a bit more about the motivation and give you some basic concepts, which I'm almost assuming most of you have at least heard about, but I'll just show my notation. And then very quickly overview the other types of solvers. IHS solvers are definitely not the only approach to MaxSat, and there are other solvers that are really good as well. but then I'll spend most of my time focusing on these implicit set solvers. And I'll sort of, since the goal here is to get to this abstract cores, I think the most difficult part about understanding abstract cores is just phrasing the IHS solver in the correct way. So I'll sort of go over the algorithm in two different ways, working towards the definitions and the way of viewing the IHS algorithm that's most suited for understanding abstract cores. And then the last part will sort of just simply follow from that. All right, so first, this I'm hoping most of you know, the Boolean satisfiability problem. We're given a propositional logic formula and we want to know, is it satisfiable? Is there a model that satisfies all of the constraints? And this has, of course, been shown to be a very great success story, as my slides say, computer science. And there's been tremendous improvements in SAT solvers starting from the mid-90s. And nowadays, these CDCL SAT solvers form core decision procedures in various different applications, including MaxSat. And in addition to finding solutions or satisfiable models, especially MaxSat makes good use of the fact that SAT solvers can also prove the non-existence of solutions and give you sort of explanations or cores in a more technical term that explain the unsatisfiability and allow you to relax your formula in a controlled way to find the optimal solution for the MaxSat instance. And the thing what I find really neat is that the progress in SAT solvers has definitely not stagnated. This is sort of a plot showing on the y-axis here the number of solved instances against different timeouts on the x-axis. So you want to be as high as possible. And all of these solvers have been run on the same hardware, on the same benchmark set. And we see that the best performing SAT solver in 2002 is only able to solve like a few tens of these instances, while the winner Armin solver from last year's SAT evaluation nears 250 instances. So every year there's been improvement, and every year the winner of that year's SAT contest has been better than the winners last year. So there's definitely still interesting things going on in the field of SAT solving as well. And as I already mentioned, this development has also made SAT solvers more and more useful for solving these other computational problems, such as optimization problems. So as I'm sure most of you are also familiar with, most of the I'll take the liberty to say most of the, in my opinion, interesting problems involve some form of an optimization component. We're not just trying to find a solution, we're trying to find the shortest solution, the smallest explanation, the cheapest solution, etc., etc., etc. And this is the kinds of problems that we're working with here. And it's in this context that MaxSat has arisen as a very competitive and interesting framework for solving these problems. And as I already touched upon, every year for these MaxSat evaluations, we get more and more problem domains. So there are more and more people trying MaxSat solvers and seeing if they can be used for their problem, and then even better, submitting benchmarks to the evaluations, which in turn will allow the solver developers to make their solvers even better on those benchmarks. So it's a loop that feeds itself, and there's been lots of progress. I think last year we had 13 new domains and tens of thousands of benchmarks submitted to the evaluations. And this has sort of led to a good improvement in MaxSat solver technology as well. It's the same kind of plot as I already showed you for SAT solvers. Here, the benchmarks are the same, and the hardware is the same. And here, the lowest solver over here is the winner of the 2010 MaxSat evaluation. which solves around 200 instances maybe. And then the winner last year, which is coincidentally exactly the solver I'll be talking about in this seminar, solved over 400. So sort of following the trends in SAT solving, we're seeing good improvement in MaxSat solvers as well. And just to wrap up this motivation, I'm show you a few plots from my own work through my PhD thesis where we applied MaxSat solvers and especially these IHS solvers. This is sort of a clustering application where we are trying to find the cheapest clustering using MaxSat. And the plot here has the cost of the found clustering against different sparsities of data. So the smaller the x-axis number, the sparser the data is. And the other lines over here show the clusterings of these approximative algorithms. So we see that with MaxSat and with IHS solvers, we're able to find clusters that are significantly better, clusterings that are significantly better, have lower cost than these approximative algorithms. So it really pays off to use these complete search techniques and try to find a globally optimal solution and not just settle for an approximative algorithm.
Can you say anything about the relative running times?
With this sparse, if you go to 1, so the full data set, then we're talking 15, 20 minutes with a MaxSat solver and a few seconds with these solvers. But the cool thing about this plot, I think, is that if we then go to these sparser sets, so under half here, the MaxSat solver ran for a few seconds, so it's definitely comparable to these approximative algorithms and still was able to beat them by quite a lot. Good question, thank you. And the second sort of application that I'll briefly mention, and here I'm confusing you because now I put the instances on the x-axis and the timeout on the y-axis. So now we want to be as far right as possible. This is sort of Bayesian network structural learning. And we had a MaxSat encoding for the problem and compared it to other exact approaches, 2 based on integer programming, this one and this one, and then a dynamic programming approach. So we see that MaxSat scales, for this particular problem, MaxSat scaled significantly better than integer programming. And hence it's something you should consider whenever you want to solve a problem with ILP. You could at least think about maybe wanting to solve it with MaxSat instead.
Another question, which maybe is a bit off topic, but I'm just curious. So SAT technology is not only doing great in these academic competitions, right? But it's also used in industry, as far as I understand, like AMD and Intel and these, they will actually run SAT solvers on their new processor designs, for instance.
I think so.
Do you know, like, has MaxSat solver sort of made the jump over to actually being deployed in real world settings, or are these mostly these applications, are they still like academic quote unquote applications of real world problems? Does the question make sense?
Yeah, I think it does, and it's a good one. I don't think it's as widely sort of made a jump as SAT solvers, of course, but I've seen some beginnings of that step. I know Amazon has expressed interest in hosting some tracks of the MaxSat evaluation on their servers, and there's this work by Nadel on the so-called Mrs. Beaver solver, which I also think the application they had in their paper was very company specific. I can't remember the exact company, but it was sort of hardware checking and verification applications, which seem to be motivated by real world. So I would hope and say that we're getting there, but every year a bit more.
Okay, thanks.
All right, so then the basic concepts and definition and terminology / notation that I'll be using. So we're working with propositional formulas in conjunctive normal form. So we have literals, which are either Boolean variables x or not x. A Boolean variable, of course, takes values 0 or 1. And we have a clause that is a disjunction of literals, and truth assignments that map these variables to either 0 or 1. And truth assignments satisfy clauses if they set a positive variable or literal to 1, or a negative negation of a variable in the clause to 0. And the assignment satisfies the full formula if it satisfies all of the clauses. This, I hope, is familiar to all of you. And with that, then, the sort of theoretical standard definition of MaxSat, which is mostly studied in theoretical computer science, is we're given a set of clauses, which is a CNF formula, and then we're asked to find a truth assignment that maximizes the number of satisfied clauses. And while this is sort of nice to analyze, it's a bit impractical for modeling real-world problems. Instead, what we want to do is either or. The first extension is to allow each clause to have a weight. So we want to say we would rather satisfy this clause than that clause. This is weighted MaxSat. And then we can also consider a setting where we have some clauses that are hard, that we have to satisfy. And this is maybe the most commonly used for solving real world problems. You have to sort of specify how your solutions look, but with the hard clauses, which are the feasible solutions, and then the soft clauses encode the optimization. And this is called weighted partial MaxSat, but because that's a very long thing to say, I'll just call it MaxSat. And in this talk, my examples will be mostly unweighted, but all of the techniques that I'm going to be talking about can be extended to weighted case as well, and I'll make some sort of hints at how to do that here and there. So just to say one more time, in the problem that we're working with the rest of this seminar, we're given two sets of clauses, or two CNF formulas, the hard clauses and the soft clauses, and we're looking for truth assignments that satisfy all of the hard clauses and maximize the number of soft clauses that are satisfied. And actually, when we solve this, we usually treat it as a minimization problem. So instead of finding a solution that satisfies the hard clauses and maximizes the number of satisfied soft clauses, we're looking for a solution that satisfies the hard clauses and minimizes the number of falsified soft clauses. So this expression here, this will take value 1 if the clause C is not satisfied, or 0 otherwise. And this I'll say that the cost of a solution is the number of soft clauses that are falsified by that solution. A very simple example. We got 2 hard clauses that both have 2 positive variables and 3 soft clauses containing the negation of those variables. So now we can have a solution that sets everything to true, everything to 1, but this will falsify all of our soft clauses, so the cost is 3. But then the optimal solution is one that, for example, sets B1 and B3 to false and B2 to true. It satisfies both of our hard clauses and falsifies one soft clause, so cost 1. And this might be worth sort of keeping in mind. My main examples are mostly going to be of this form here in the rest of the talk. And I'll also shorten notation a bit and treat assignments as sets of literals. So this is the assignment that sets B1 to false, B2 to true, and B3 to false. So I'm mostly focused on like algorithms for actually solving MaxSat, but I'll say a bit about its complexity. It's fairly well known and fairly easy to show that MaxSat as a decision problem is NP complete. And MaxSat as an optimization problem is FNP complete. So you can make do with a polynomial number of oracle calls. And usually oracle in this context means a SAT solver. However, sort of to tease abstract cores, we also know that for the IHS implicit hitting set algorithms MaxSat, the worst case is actually an exponential number of SAT solver calls. So there are instances on which a basic implicit hitting set solver needs to do an exponential number of SAT solver calls. And that's sort of the main problem that we're addressing with abstract cores. So any questions about the basic definitions before I go on to overviewing solvers.
Maybe just a quick question, but I assume you're going to answer later. So you said that's the main problem we're addressing with abstract cores. So will you solve it in this talk, or will you get fewer calls and still get an exponential number, worst case?
It's a very good question. From a purely theoretical point of view, we will solve it. From a practical point of view, we won't. I'll talk more about this, but it turns out that abstract cores offer you a solution where you can drop the number of required calls to polynomial, but instead you're going to end up with potentially exponentially harder SAT solver calls. So you're sort of switching the complexity from the number of calls to the complexity of those calls. This will make hopefully more sense when we get to that. But on paper, abstract cores can drop the number to a polynomial number. In practice, that still wouldn't be effective for solving actual problems. We tried this, but it's a good question. Thanks.
Do you want to say anything? Maybe we're just getting ahead of ourselves, but when you would need several calls to the implicit hitting SAT solver, would this be something like saying that you have some constraint trying to encode something like half of the variables have to be true, and then you would try out like all subsets of one variable to few?
Exactly. This is the sort of typical example. So instances where you're sort of saying, I have to falsify at least half of the soft clauses, then any set of soft clauses that has that contains at least half of the elements will be a core, and there's going to be like a subset. The exponentiality comes from the fact that any subset of soft clauses will be a core, and this is the typical example, which I'll talk more about in the last part of the talk as well. Maybe I've prepared too much material on the basic IHs because we'll go through that a bit faster then. Okay, so a MaxSat solver, if there's anyone who doesn't know, a MaxSat solver is just an implementation of an algorithm that computes an optimal solution to MaxSat. And here we're working especially with complete solvers. So given enough time and given enough memory, we're guaranteed to get the optimal solution. And nowadays, there are many MaxSat solvers available that you can just download and push a button to run on your instance. And most of them, including the IHS solvers, rely a lot on the CDCL SAT solvers. And since 2017, a nice thing is that the solvers also have to be open source. So any solver, if you go to the evaluation homepages and download the solvers, you can also get their source code and start building on them yourself. And very roughly speaking, complete MaxSat solvers can be divided into two parts. There are these branch and bound solvers that are effective on small but hard instances, and typically these random instances, and as such, are not the focus of this talk. And the second part are the SAT-based MaxSat algorithms that make use of SAT solvers internally. And this can be divided, again, roughly into three different types. The so-called model improving solvers that use a SAT solver to extract MaxSat solutions that are of increasing quality, so lower cost. Whenever you get a solution, you ask the SAT solver for one that has lower cost, and then you keep on going until the SAT solver says, well, there are no more solutions of lower cost, and then you're done. The second large group are the so-called core-guided solvers, which instead work by extracting small subsets of unsatisfiable clauses that we know that any solution has to falsify at least one clause of. And then you relax your instance in a controlled way to allow one of the core clauses to be falsified in subsequent iterations. And then you keep going until you get a solution. And then the implicit SAT solvers that I already mentioned are sort of a hybrid approach in between the two, where you decouple MaxSat solving into core extraction and optimization. And For explaining them, I'm going to need to define cores and heading sets a bit more precisely. And then I'll use this part of the talk to sort of go over the first way, the initial way in which these solvers were defined, which I hope, my aim is that that gives you the intuition for why they work before we move on to the sort of more modern way of defining them, which then also lends itself better for defining abstract cores. So now then, a core, the term I've used a few times already. A core is simply a subset of the soft clauses that is unsatisfiable together with the hard clauses. So here, if we have the same instance as before with 3 soft clauses, but it's fairly easy to see that already these 2 soft clauses cannot be satisfied together with the hard clauses. You have the clause here that says that at least one should be true, and then soft clauses that say that both should be false. And a core, we say that it's an MUS for minimal unsatisfiable subset if no subset of the core itself is a core. So if every subset is satisfiable together with the hard clauses. So this is also an MUS. And at this point, I'll shorten notation even more and just use these comma-separated tuples for clauses.
And Jeremias, just another comment for people joining from the theory side, I guess, is that you kind of already mentioned it very briefly, but in fact, without loss of generality, you can assume that your soft clauses are always these unit clauses with only one literal.
Yeah,
right.
Yeah, you can. I'll talk more about that as well in the middle. But yes, this is a nice format, and for the moment we'll just take it as is. But you can use this, and there's a good reason for why you would want to sort of assume this.
Okay.
So now then, the second central concept for these IHS solvers are so-called heading sets. So we have this instance, the same as before. And then we take a collection of these cores. So here, this one has 2 MUSs or 2 cores. The first one we already saw, and the second one contains not B2 and not B3. And now a heading set is simply a collection of soft clauses that has non-empty intersection with all of the cores. So they're always defined with respect to some set of cores, or with respect to some collection of cores. So here, we have one example that has not B1 and not B3. So we see that it has non-empty intersection with both of these cores. And we say that it has cost 2 because it contains 2 elements. In this unweighted case, we could, of course, again, we could have weights here, but for simplicity, we'll go with non-weights. And then another heading set over both of these cores just contains B2. So this one has cost 1. So we see that there can be many different heading sets. And what we're really interested in are these minimum cost heading sets over a collection of cores. So here, this is an example of a minimum cost heading set over this collection of cores. And what does this have to do with MaxSat? It's fairly easy to show that if you have all of your cores, if you have a collection of all cores or all MUSs at least, and you then compute this minimum cost heading set over that collection, then there exists a solution to the MaxSat instance that falsifies exactly the soft clauses in your heading sets and satisfies the rest. So here, as we already saw, the minimum cost heading set contains the one clause with a negation of B2. And there's a solution that satisfies all other soft clauses and the hard clauses and falsifies exactly the one soft clause in the heading set. And this is sort of the underlying idea of implicit heading set MaxSat solvers. And in order to turn this into a practical algorithm, we have to, the key insight is we don't actually need to compute all of the MUSs beforehand. For many instances, there might be exponentially many of these MUSs, and extracting even one is a very difficult problem. It's DP complete. So we don't want to extract all of them. Instead, we want to extract a fewer number of them, any number of them, compute a minimum cost hitting set over that collection, and then check if there exists a solution that falsifies exactly the clauses in the hitting set that we have and satisfies all of the rest. And if there is, then that solution will be optimal for the MaxSat instance as well. And this is sort of the main principle on which IHS solvers are built. So during search, you accumulate a collection of cores, and then on every iteration, you compute a hitting set over your collection, and then rule out the clauses in that hitting set and check with the SAT solver, are the rest satisfiable or not. This is the first way in which implicit hitting set solvers are presented. In the second go around on this, I'll show you a few improvements on this basic formula, but in principle, this is how it works. And the way in which the hitting set is computed is then by integer programming. We form this integer program, and we take these variables, which are defined to be true if the corresponding clause is in the hitting set. And then we say minimize the sum of weights, or the number of, in this case, of these variables set to true, such that at least one from every core that we have is set to true. So we're minimally trying to hit the collection of cores that we have.
So I realize there's a real risk that I keep running ahead of you, and if so, you just tell me to shut up at some point. But if you look at this problem, interestingly, that's a weighted MaxSat problem, right?
Yes.
But you wouldn't want to feed it to your MaxSat solver? You'd rather have an IP solver?
There's nothing saying that you couldn't. I actually will not talk about this, so this is a good question. And we've sort of discussed this with Fahim, and he has tried. So far, there's a very pragmatic reason for why this isn't done, and it's the fact that for these types of problems, IP tends to be better. So if you try to solve it with a MaxSat solver, your performance is worse. But in theory, there's nothing, any way you could compute a hitting set could in theory be used as part of this algorithm. So far, integer programming and Cplex seems to be the best we have for running times. But if you, especially for unweighted hitting set problems, if any one of you knows a good algorithm for computing hitting sets in the unweighted setting that's better than Cplex, please let me know, and we'll work something out. Yeah, and so as this is sort of touched on this fact. So why you would want to do this is sort of just combining the best out of these two different technologies. SAT solvers are really good at proving unsatisfiability and computing you these cores. And IP solvers, in turn, are better at optimization and computing, like numerical reasoning, finding you the minimum cost hitting sets. And with all of this, we then get the first sort of complete view of how you could, of an IHS solver. You start by sort of initializing a hitting set, empty hitting set and an empty collection of cores. And then you ask the SAT solver, are my hard clauses together with my soft clauses, together with those soft clauses that are not in the hitting set, satisfiable or not? They most likely won't be in the beginning. And you get a new core, which you add to your collection. And then you go to the IP solver. Give me a hitting set over the cores that I have right now. And it will give you, update your hitting set. And then you just keep going until, I'll give you the concrete example in the next slide, but then you keep going back and forth until you get SAT. And at the moment that you get SAT, you know that solution. The intuition here is that you're sort of asking the IP solver to minimally hit all of your cores. So as soon as you find a solution that minimally hits your cores that you have, that still and satisfies all of your hard clauses, then you're done. Then you have an optimal solution. So you don't have to wait until you've computed all of the cores. So let's see the concrete example. You initialize the set of cores to be empty, and then you start your loop. First, you compute a hitting set. Here we don't have any cores yet, so we get an empty hitting set. And then we ask the SAT solver to find me a solution that satisfies the hard clauses and all of the soft clauses except for the ones in this empty hitting set. So all of the soft clauses in the first iteration. And the next part of the talk, I'll talk more in detail on how this is actually done. But for now, you just take my word for the fact that the SAT solver can not only say unsat, but also give you a subset of the soft clauses that correspond to a core. So here it can give you this core that we already saw. And then you add that to your collection, and you go back to the IP solver. And then the IP solver will find you a minimal hitting set that could contain, for example, not B1. And then you go back to the SAT solver, and now you ask it for a solution that satisfies the hard clauses and every soft clause except for not B1, because that was in your hitting set. This is still not doable. SAT solver will find you a new core, for example, not B2, not B3. And now you can go back to the IP solver, and here we see that the new hitting set that you find doesn't necessarily have to have a higher cost. So here we can still hit all of the cores with one clause, this B2. So the cost of the hitting set will be non-decreasing, but it can be the same. We go back to the SAT solver and now ask it for a solution that satisfies the other soft clauses. Still not possible. But now the next time when we go to the IP solver with these cores over here, we now get a hitting set that contains at least two clauses. Go back to the SAT solver and ask it for a solution that satisfies the other ones. And now it says SAT, and we get this solution, and we're done. And this is sort of the most simple way of describing an implicit hitting set algorithm. Does anyone have any questions about that at this point before we look at how this is actually done nowadays? If not,
well, actually, so can you see anything about the relative costs of like running the MaxSat solver to find the core and then running the IP solver to find the hitting set? Is it like is 50-50, or is one of the components clearly more expensive than the other, or it would varies a lot? Or
it varies somewhat, but in general, the hitting set computation is the bottleneck. So on most instances, the difficult part, on most instances from practical applications, the difficult part is computing the hitting set. Of course, if you give it like some sort of an optimization version of a pigeonhole formula where you're asking the SAT solver to prove sort of pigeonhole, then the core extraction will get a lot more expensive. But on the benchmarks that correspond to sort of real world applications, the hitting set is the one that's costly. And the core extraction is very. If there's anyone here who has more familiarity with MaxSat solvers, the nice thing I'll say here is that still, the nice thing about this approach is that you're not changing your underlying formula. Every SAT call that you make is going to be on a subset of your original clauses. Other solvers, such as the core guided ones, need to sort of reformulate and change the underlying MaxSat formula to make the SAT calls more difficult. So they tend to get more expensive as during the search. Here, if anything, your SAT calls are at most as expensive and sometimes even get cheaper during the search, depending on how large your hitting set is.
I have a small question with the core extraction.
Mm-hmm.
Let's say you're in a weighted MaxSat, then I guess your your core extraction, it would be more interesting if you have it targeted, no? Because if you do a regular core extraction, you find you have something that's satisfiable, and then you shrink it, and then you have some mus. But it would be interesting to have a better mus, no?
Yeah. Yes. In principle, yes. So you could, by sort of varying which ones you can vary the set of subclasses you're trying to find a core over. So you can try to target more expensive ones. And we've done a bit of those tests. And for these core guided solvers, that's very essential for making them work. Interestingly, for IHS, we found that it doesn't really improve that much. The sort of implicit hitting set solver handles the numerical reasoning well enough, so you don't have to do that much of this targeting. But it can be done, and I could see it helping on some instances. But again, on this sort of, in general, it doesn't have that much of an effect here. But that's a good point.
Okay, thanks.
If there are no more questions at this point, I'll then move on to the second part, see if we can get through this before the break. And here, my goal is to sort of what Jakob also hinted at, is to define MaxSat in terms of these blocking variables. So show how the assumption of soft clauses containing unit negative literals can be made without loss of generality, and why we would want to do that. And then sort of redefine the whole algorithm in terms of bounds. So it's a bounding procedure instead of this in terms of sort of correction sets where you stop when you get sat. So this sort of touches on how cores are extracted in practice. Most, I would almost like to say all of the SAT solvers that I'm familiar with implement an API for solving under assumptions. So what does this mean? What this means is that we have these constraints, these clauses, and we can then give the SAT solver sort of assumptions in the forms of literals. So a set of literals, and ask it for a solution, a model to the formula that satisfies all of the literals. So we ask it for something that satisfies all clauses, but also sets B1 to false and B3 to false. And that it can happily do with, for example, this formula. But if we then try to ask it for a model that satisfies assumptions that cannot be done, so here, for example, we're asking it for a model that sets all three of these to false, it will say unsat. There is no such model. There is no such model. I'll talk about what else this can give us on the next slide, but I'll just briefly say that another way of looking at this is to see it as partial assignments. So you can view the set of literals as a partial assignment, and you're actually asking the SAT solver for an extension of that partial assignment to the full formula. And what we do in MaxSat is make use of these unsat results to get the cores. So CDCL SAT solvers, the way in which they determine unsatisfiability is by learning an empty clause. So in short, you're learning a conflict at decision level 0. And what you can do with assumptions is then, once you have this conflict at decision level 0, you can go back to your assumptions and check which subset of them were necessary to get this conflict. So you basically propagate them one by one and stop as soon as the solver says conflict. And then the number of assumptions you propagated at that point, that corresponds to your core. And how you make use of this in MaxSat is that you add an assumption variable. So when if you have a soft clause, you can add a new variable to that clause, and that variable will then sort of control this clause. So if we set the assumption variable to 0, we switch the clause on. We're saying you have to satisfy the clause because this is going to disappear. And if we set the variable to 1, we switch the clause off because this extended clause will disappear from the formula. It's satisfied. So what we do is then, to get a core, we take our hard clauses and our soft clauses extended with these assumptions, and we invoke the SAT solver while assuming all of the assumption variables to false. So asking it to satisfy all of the soft clauses. And if the result is unset, the SAT solver can then do the thing I talked about a minute ago to give us the subset of the assumptions that were sufficient for explaining unsatisfiability. And that subset of assumptions can then be mapped back to the soft clauses that we originally added them to. And that is how we get the final core. And this is basically the way in which any MaxSat solver that I'm aware of extracts cores. So a concrete example, same as before. We extend the soft clauses. We invoke the SAT solver while assuming the value of all assumption variables to 0. We get unsat. We get a subset of assumptions containing the first and the second, which we then map back to the core. And here's sort of the thing that was mentioned before. If you now look at this, there's no real reason for why we would have to add these assumption variables. We can just instead use the original variables in these soft clauses as assumptions. And in fact, it turns out that it's for explaining many of the MaxSat algorithms, it's actually better to just assume that we've already extended all of our soft clauses with assumptions, and then treat the assumption variable to find MaxSat with these assumption variables instead. And the term that's usually used instead of assumption variable is a blocking variable. So here is sort of the clause-based view that we already had, hard clauses and soft clauses. But instead we can define MaxSat in terms of clauses, hard clauses, and blocking variables. So in essence, we're assuming that any soft clause that we might have had that's not a unit negative soft literal, we just extend with a new variable, put the extended clause as hard, and add the negation of the new variable that we used as soft. And we say that all of these variables that would appear in soft clauses are these blocking variables. And now we can, instead of assigning a weight to soft clauses, we just assign weights to these blocking variables. So we're looking for a solution that satisfies the hard clauses and minimizes the number of blocking variables set to true. If you see this link, setting a blocking variable to true falsifies as the corresponding soft clause. And this next definition is maybe the most important one for understanding abstract cores. Now a core is then a clause over blocking variables that's entailed by the hard clauses, or the clauses in your formula. So here's the previous definition that we had. We say that the hard clauses together with not B1 and not B2 is unsat. This is equivalent to saying that any solution that satisfies the hard clauses has to set either B1 or B2 to true. So we can see the core as the clause over B1 and B2 that's entailed by the hard clauses. And for understanding abstract cores in the second part, this is sort of the way in which you should think of cores. So cores are, that's why I'll say it again, cores are clauses over blocking variables that are entailed by the constraints in your formula. If anyone has a question about this, this would be a good point to ask. And then a heading set is then a set of blocking variables given a set of cores, so clauses. A heading set is it's a set of blocking variables that has non-empty intersection with all of the clauses.
A question maybe somewhat related to what Emilio asked. So if I understand correctly, with this assumptions interface to a SAT solver, you run it under some assumptions, and either you get SAT back and then you're happy, or you get a core, like you get an explanation that no, you can't, like you get a sub assignment that cannot be extended to a satisfying assignment, right? That's,
yes.
And the point is how there might be several explanations. Do you somehow interact, and maybe your SAT solver gives you, I don't know, potentially a slightly larger explanation that would actually be the case if you want to somehow massage the core or minimize it or something? Would that be happening on the MaxSat solver side, or you're assuming that the SAT solver already works on giving you the best possible core back?
We're not assuming that, because that's generally not the case. We don't require it. The algorithm does not require MUSs, and there are some lightweight heuristics. Okay, maybe I see that I might have misunderstood the earlier question. There are some lightweight heuristics that one can use. So say we get one core, we can then just call the SAT solver again with the assumptions in the core and sort of hope that it will find us a subset of those that's going to be a smaller core. In general, if you would want to get sort of a guaranteed MUS, you would have to do lots of these SAT solver calls to check for every single variable in your core, whether or not it's actually needed. We don't do that because it's too expensive and not needed for the correctness of the MaxSat algorithm. But some lightweight stuff is done, sort of hoping to get a smaller core.
And the reason why you might want to do some lightweight stuff is as you said, that the IP calls tend to be expensive.
They tend to be expensive, and the IP solver does not know anything about the other structure. If you give it a core that's unnecessarily large, the IP solver won't know that it should hit, which part it should or should not hit. For it might be equivalently good to hit any single clause. While it turns out to actually get the SAT result, we have to hit specific ones.
Okay.
So now just the same thing in terms of blocking variables. Now instead of extending with quote unquote unnecessarily extending all of the clauses with assumption variables, we just invoke the SAT solver while assuming all of our blocking variables to false. And the SAT solver says unsat and gives us back a subset of our assumptions, or actually, I like to see it as a subset of negated assumptions that says B1, you cannot set both B1 and B2 to false and satisfy all of your hard clauses. So you have to set either one to true. So this is exactly a clause over blocking variables that is entailed by the hard constraints. And why this is even more nicer for an implicit hitting set solver, you can sort of combine the check with the hitting set and the core extraction. So you don't have to assume all of your blocking variables to false. Instead, you assume every blocking variable not in your hitting set. And now the SAT solver will either tell you that all of the blocking variables that are not in your hitting set can be set to false, so the corresponding soft clauses, if you want to think of it that way, can be satisfied, or you get a new core that's a subset of this. So the new core is guaranteed to not be in your hitting set, and then you get something new for the IP solver to hit, and hence you progress the search. So here you would get this core because this is not a subset of your hitting set. And now I'm going to end this part with the same example again from a slightly different point of view. But before that, I'll still say that sort of more quote unquote modern way of phrasing IHS is in terms of bounds. So during search, you can actually, turns out you can get both upper bounds and lower bounds on your optimal cost. The upper bounds come from core extraction. Instead of going to the IP solver after each individual core, you can keep extracting cores and try to find as many as you can that lie outside of your hitting set. And you keep going until the SAT solver doesn't find any more cores, and it reports SAT, and it also gives you a model. It doesn't have to be an optimal model, but it gives you a solution that satisfies at least your hard clauses. And hence you can look at the cost of that solution, which you can, and get an upper bound for the optimal cost of the instance, because we're minimizing the cost. So any solution, the cost of any solution would be an upper bound on the optimal cost.
One question here. What do you mean by keep extracting cores? Do you mean enumerate all of them, or do you extract them in some systematic way?
The next example should show this, but basically we're doing a disjoint set of cores that from outside of the heating set. So once you get a core, you add those, you stop considering them and try to extract a core from whatever is left, and then you keep going.
Not just one literal, but all literals in the core you found, you remove from your assumptions.
All literals, yes. This is based on experimental evaluation showing that it's better.
Okay, so in your toy example you had before, once if I find a core like the B1 or B2, I have to set one of them to true, then you throw both of them out and you adjust it, make assumptions on B3 and B4.
This is exactly what will happen on the next slide here.
Sorry.
And then I'll get back to part. Maybe we can see the example and then you can ask if it's still not clear after that. So from the other direction, then the lower bounds are going to come from your heating sets. So it's fairly easy to see that if you have any set of cores and you compute a minimum cost heating set over them, the number of elements in that heating set is going to be a lower bound on the optimal cost. The reason for this is that your optimal solution has to falsify at least one, or has to falsify at least one literal, or set one blocking variable from any core to true. So any set of cores will have at least one element from each core set to true by the optimal solution, and hence it will be the size of the heating set over that set will be a lower bound. So here's now what I already teased, that the same example from this more modern bounds-based view. So now we initialize not only the set of cores, but also an upper bound to infinity, a lower bound to 0, and the best solution, which is going to correspond to the one achieving the upper bound. And we don't keep on going until we get sat. We keep going as long as the lower bound is different from the upper bound. We compute the heating set exactly as before. And here I'll remind you all that we could have weights in the IP, and this would solve weighted MaxSat. First, we don't get a meaningful heating set because we don't have any cores, so the lower bound stays at 0. And now we set up our assumptions for the SAT solver call. So we look at all of the blocking variables that we have. We remove the ones that are not in the heating set. So the first time around, we're going to have them all. And then we invoke the SAT solver while assuming all of our assumptions to false. SAT solver says unsat and gives us, for example, the core containing B1 and B2. So we just remove both of those from the set of assumptions, and then we invoke the SAT solver again. So now we're asking it for a model that sets B3 and B4 to false, and we don't care about what it does with B1 or B2. It again says unsat, and we get the core B3, B4. And now we're asking it, we remove the new core from the assumptions and invoke the SAT solver again, this time without any assumptions. And the SAT solver says sat and gives us back some model of the formula. For example, this one, which has B1, B3 to false, and the two others to true. Now we check the cost of this assignment. It sets two blocking variables to true, so it has cost 2. So we know that the upper bound on our optimal cost is 2. And then we store all of the cores. And now we check, is our upper bound equal to our lower bound? It isn't, so we start over from the beginning, from the start of the loop. Now we have 2 cores that we need to compute a heating set over. And then there are a number of different heating sets that we might get. Here's one containing B1 and B4. And since it has 2 elements, we can set the lower bound to 2 and immediately terminate. So notice especially that removing B1 and B4 from the assumptions would not make the instance satisfiable. So in more technical terms, this is not a correction set of the instance, but it is a minimum cost heating set over our set of cores. So it is a lower bound, and we already have a solution that can achieve the lower bound, has the cost of the lower bound. So we can just stop and return this solution. Does this answer your question, Bart?
Yes and no. So it answers the part I asked, but not the part I thought. I know what's happening now. But so what I'm still wondering about is why. So what's special about the disjointness? So what I see is that these disjoint cores here, they provide kind of independent extra constraints on your hitting sets.
Mm-hmm.
Is there more that's going on, or?
This is how I mean, why we do this and nothing else is just based on experimental evaluation. And my best explanation for this is exactly as you say. With disjoint cores, you're forcing the hitting set to hit at least in more places. If like earlier we had a core B1, B2, and then B2, B3, and the hitting set will happily just hit B2 and not give you, by forcing it to do this, we get the hitting set that has 2 elements faster.
Mm-hmm.
But there's no theoretical reason, like we don't have to do disjoint cores, it just turns out that it's effective.
And do you know if it's always effective or that it's, well, not always, of course, but I mean, in practice, typically effective on instances where the hitting set part is expensive, but the set part is cheap?
It is, I would say it's always. Typically, I think here, my next slide actually had this. I think it's typically effective because termination, while termination does not require a correction set, it still requires the lower bound to be pushed up to the optimum cost. So we still have to have some hitting set that achieves the lower bound equal to the optimum cost. Before that, we cannot really terminate. So that's why we would want the hitting set solver to hit in many places as fast as possible, because we still have to hit all of the cores at some point. So okay. We want to steer, yeah.
Mm-hmm. So there are two parts of the effectiveness. On the one hand, you might get faster to your optimal value, and on the other hand, you might faster be sure that you are at your optimal value, right? So that and the being sure has to do with the lower bound. Yeah, sorry, I don't have any more questions. I was just thinking out loud.
Basically, once we have a hitting set that achieves lower bound, typically the upper bound will go down fast, because especially if you have a correction set, it's one sat call, and then you get the upper bound down. So the hard part is getting lower bound.
But I'm also a bit curious about this, especially since I guess, you know, in the interest of full disclosure, we tried this independent course in our solver and didn't get it to work, and we don't know why. But it's, of course, that's a core guided solver, so it's kind of different. But could it all, I mean, is there any adaptivity here for you? Because intuitively, like in the very first call, you can expect that, well, there are many cores around, and it sort of doesn't make sense to disturb the IP solver when you haven't explored a lot of the core space, as it were. Like, why don't you just a quick and dirty, like, you know, find something to actually, you know, get the IP solver to work with, and that's a quick and dirty way to collect some cores from all over the place. But it could be like, I mean, maybe later on in the search, one could imagine that you find a new core, and then the next solver call will always be sat, and if this keeps repeating all over and over again, would you switch this off and then immediately call the IP solver, or no, you don't have to do that?
If the next, we could, we don't, and I would say that the situation that you describe, if the next sat solver call is sat, it's typically very fast. The sat calls are very fast, so it doesn't really hurt too much. But then again, if we just try to if we get one single core and then just go to the IP solver without even trying to get a new core, it might be that the IP solver will just, in a certain sense, if we have a hitting set and there are a number of MESs outside of the hitting set, we still need to hit all of them. So if we can extract all of them without going to the IP solver, it usually pays off.
Okay, so I guess this is somehow difference also between theory and practice, that not all Oracle calls are equal. You're saying that this extra Oracle call on the SAT side is, in your experience, it's a cheap call, so it's like...
Yeah, I mean, when you do this loop, you're removing assumptions all the time. So in sort of informally speaking, the SAT calls are going to get easier and easier because you're relaxing, you're asking. And then the final call that gives you SAT is typically very fast.
That's a good point, yeah.
And then I'll say, before I said the second part is going to be about abstract course, but I'll say that there are a few other sort of additional heuristics. You don't have to compute a minimum cost hitting set. You can just compute, especially in the beginning, you can compute any hitting set and then just continue extracting cores. You can update your lower bound only with a minimum cost hitting set, but when you haven't yet extracted enough cores to get close to optimum, it sort of doesn't pay off to spend a lot of time computing a minimum cost hitting set that won't do you any that much good. And then this has also been extended with standard techniques from IP solving. You can consider the reduced costs of your hitting set instance, which is sort of maybe an answer to why you would want to do it with an IP solver, because it gives you more techniques that you can then use to fix variables in both of your instances during search. And most of these techniques, we've seen this now twice. And I would say if you try to implement it based on my first presentation, it will not work. So you have to do a number of these things to get this approach to actually work in practice. And this is sort of summing up implicit hitting sets on the whole. They are really good and one of the top contenders. And for solving MaxSat instances specifically, this is better than just converting it to IP and running an IP solver such as Cplex. And here I would say we might want to, this is the sort of 2/3 down that I talked about. The last part is going to be about abstract course. Do you want to break at this point?
I think that sounds good to me. A chance to stock up on coffee. We can also open up for some further questions. I guess we had a lot of questions already, but questions are nice. So while others are thinking about their questions, I wanted to ask one. So you can sort of think of this as you're having your MaxSat solver master that is like running an IP solver slave, as it were, right?
Yeah, or a SAT. Well, MaxSat is sort of the combination. So you have a SAT solver.
Okay, whatever. But like one could imagine, I guess, or I don't know, if this has been done, like somehow integrate this into an IP solver and make these kind of aggressive assumptions. And
I don't know if this has been done. I don't think so. There's some work in sort of this CDCL techniques in IP solving in CP a few years ago, conflict-driven IP or something that was called. I haven't followed up on how effective that is. That is sort of probing. It could be interesting. I can't say too much more about it, but
okay,
sure.
Any other questions before we have a break?
I have a question. Hello.
Hey.
So I don't know much about this, but you in your presentation you had a hard instant. How did you call them? The hard clauses and the soft clauses.
Mm-hmm.
And for me, a more intuitive way will be just to have some weighting on all the clauses, integer weighting, say, and which is this is a specific example of some integer weighting where the hard clauses get very high weight and the soft get weight 1, and then you sort of try to optimize. And what I was trying to figure out as you were talking, if the ideas will work in this setting as well, and I couldn't. So the way you explained it, somehow this 1 and infinity weighting was important, and the question is it important or?
In theory, no. In practice, yes. In theory, you can do exactly as you said. You can give the hard clauses a weight high enough to make sure that it's always better to falsify all of your subclasses instead of falsifying a single. So you can sort of achieve this. But if you would try to run, for example, on this solver, this would then mean that you would have to somehow have assumptions on all of your clauses, which would make the SAT solver calls in some sense harder. You're asking the SAT solver to do more work. You're sort of creating this false situation where you're asking it to optimize over all of your clauses when you know that you'll never want to. If you know that you'll never want to falsify these clauses, then it's better to treat them as sort of separate in some sense, as hard. But in theory, like if you want to, in theory, you could just have weighted clauses, and then you could, the setting where you don't have hard clauses is captured.
But then so if you have some arbitrary weighting on the clauses, is there some, so the way you used integer programming was specific for the specific weighting you worked with, which is like, is there some way to assign weights that correspond to the general, or so, right? You need to assign a weight to the heating set.
Yes. So here I was just assuming weight 1. But you could have, if you have weighted clauses, you just add those. And then the weight of your heating set is just the sum of the weights of these variables. So if you wanna, that's
okay.
So if you want to have weight, if you wanna assign weights to all clauses, you would then still add this assumption variable to all clauses, and then that assumption variable would have the weight in it, in order to be able to do core extraction, basically.
Okay, so just summarize it to myself. The theory is the same, but if there is general weighting, it will probably take too long.
Yeah.
Thank you.
But there's also this thing about when you run the SAT solver with assumptions, right? You're only guaranteed to get back something that contradicts your assumptions, and you really want to have a core over the soft clauses. And
yeah,
you
but
wouldn't like have that guarantee if you assumed everything to, if you needed assumption variables for everything.
You would, in some sense. Okay, I did not say this, so it's good that it came out. We're implicitly assuming that there are solutions. If your hard clauses are unsat, then you're doing SAT, not MaxSat. So if you have that assumption, so that you have some feasible solutions, then you would never get a subset containing only assumption variables corresponding to your quote-unquote hard clauses, because in that case you wouldn't have any solutions.
That's true, but you could, okay, yeah, but you could potentially get a mix, right? I guess you could trim it, but
yes.
like
you would get a mix, and then you would spend lots of like extra effort in your IP solver asking it to consider solutions that you will will not be the ones you want anyway. So that's sort of what I mean by that. It could be done, but it would in practice not pay off.
So maybe let's take, what do we say? Should we try to be back like in 9 minutes? So Central European Summer Daylight Saving Time 15:25.
Sure.
Okay, so let's have a almost 10-minute break. So we are back after the break. The suspense is enormous, but we're finally going to hear about the main topic of today, which are the abstract cores. So without further ado, please.
Thanks. All right. So this is now a very recent improvement to the algorithm that I spent the last hour talking about. And what I'll talk about in this last section is then in more detail, what are the weaknesses of the implicit sitting set-based approach? And what are abstract cores and how do they try to address these weaknesses? And then how can we add abstract cores to the algorithm, and what effect does it have? And I'll actually tease the last part already. This is one of these sort of old school cactus plots where you want to be as far right as possible. The community has actually started slowly changing to the other one. And here, the yellow line is a basic IHS solver. So the stuff I've been talking about. And when we now add abstract core reasoning, we get the blue line over here. And then when we pull some more tricks, we get the black line. So in short, we take an IHS solver and we push it past the core guided solvers that were the best performing ones in the 2019 MaxSat evaluation. So first, for motivating this course, already in the original PhD thesis proposing this approach for MaxSat, they showed that there exist MaxSat instances on which the IHS approach needs to extract an exponential number of cores. And the form of the simplest one is one that Jakob, I think, already mentioned. So we have hard constraints saying that at least R of these R blocking variables need to be set to true. So this corresponds to falsifying a soft plot. And what this means is that if we take any subset of these blocking variables with at least n minus R plus 1, so if we have to set R variables true, we can at most set n minus R variables to false. So any set that has more than that element will always have at least one of them set to 1. So in other words, the clause over those will be a core. So if you now instantiate to concrete numbers, if you set n to 8 and R to 4, this corresponds to saying that any subset of blocking variables with at least 5 elements will be a core. And on the other hand, any subset of blocking variables that has less than 5 elements will never be a core, regardless of which elements those are. So it doesn't matter which blocking variables you have. The only thing that matters is how many of them do you have. And it can be shown that an IHS algorithm needs to actually extract all of subsets of this size from this instance before it can terminate. And if we get the exponential result by setting R to something close to half of n, then this number here is going to be exponential in n. And the intuition for why this happens is what we called exchangeable in the paper with Fahim. A core is defined only by how many blocking variables are in it, not which ones there are. And a very short overview on how you would show this fact is that if you have some subset that has more than n minus R plus 1 elements, then that's not collected yet, that we haven't seen yet in the algorithm. Then we can take every blocking variable that's outside of that set, and it will hit every core that we have. There cannot be any single cores inside of this S because every core is at least this size. So we can take everything else and then we can hit every core, and everything else will have R minus 1 elements, n minus this. So it's going to be lower than the optimal cost. So we cannot terminate because in order for the algorithm to terminate, IHS to terminate, we have to get a hitting set that has the same cost as our optimum. So we need to extract every subset of that size. And this weakness is actually seen in practice from the 2019 evaluation. Here, MaxHS is an implementation of the basic implicit hitting set solver. MaxHS 4.0 is the implementation with abstract cores, as we propose here, and RC2 is a core-guided solver. And there are 2 benchmark families that have exactly that structure that I showed you. And we see that without abstract cores, the solver is only able to solve 3 of them in an hour. And with abstract cores, it's able to solve all of them. And the core-guided solver is able to solve all of them. So it does actually pay off, and we can see this happen in the evaluations, this weakness. So the central question here is, does there exist a compact representation of a large number of cores that the IHS algorithm can reason over? And sort of a natural idea here is to ask, well, since in the bad instance that we saw, it only matters how many blocking variables we have. It doesn't matter which ones. So what happens then if we introduce new variables that basically count how many variables we have? And this is similar to the kind of summation variables that are used in correlated solvers.
Basically, from a theory point of view, what you can say is that your collection of cores so far, I can view it as a CNF formula over these blocking variables. Yes.
Mm-hmm. Yes.
And so you have this CNF and you don't like it because it's very large.
Yes.
And you want to somehow implicitly or explicitly rewrite it to some more succinct form that represents the same function. Is that sort of a legitimate way of describing the problem?
That is a good way of describing. But we want this rewriting to we want to be able to do it algorithmically, so automatically and not beforehand. And
also by only having partial information, I guess. It's not like you're given all of the cores, you're just discovering them along the way.
Exactly. So what we do is then, this is sort of the two parts. The first part is what we do once we identify interesting subsets, and the second part is how do we identify interesting subsets of these blocking variables. So first, what we do. So say we take a subset, say we have identified B1 to B5 to be quote unquote interesting. And then we introduce new variables and clauses, constraints that define them. This is exactly this is counting how many of the blocking variables in this set are set to true. So SABI is true if and only if there are at least I variables in this set to true. And this, even though I'm showing it as a cardinality constraint, this can be encoded as CNF. And actually in this algorithm, we're going to end up encoding it as a CNF for the stat solver and adding it as a cardinality constraint into the IP solver. So now if we look at a clause that contains blocking variables and potentially these counting variables, since it has this SAB3, it means that any subset, this is similar to the argument from before, any subset of this AB set that has at least 3 elements will always have at least one set to true. This variable here says that at least 3 of them are set to true. So from this set, there can be at most 2 that aren't. So this one clause here corresponds to a large number of clauses over only blocking variables, which are obtained by exchanging this variable with any subset of the AB that has 3 elements. So now, to make this a bit more concrete, we say that the set AB is an abstraction set. The variable SAB is an abstraction variable, and the definition of the abstraction variable is this equality here. And now an abstract core. Recall that I said that core should be thought of as clauses entailed by constraints. An abstract core is now a clause containing blocking variables and counting variables or abstraction variables that are entailed by the hard constraints and the definitions. And even though in this work, we only consider this summation as a definition, there's nothing in the framework that stops you from considering something else. This is, for example, could be used for symmetry breaking. And now we're nearing the question that Bart asked in the beginning. It's fairly easy to show, sort of like I already did on the previous slide, that if you have an abstract core containing these count variables, it's going to be equivalent to a very large number of normal cores. You can just exchange any count variable with a subset of the abstraction set.
But this is specifically for that problem that we saw, right? In which everything of the same size, or is this a general theorem?
This is a general theorem. Sort of the part I'm still glancing over is how do you get this abstraction set? But if you have an abstraction set, and then you extract abstraction cores over that abstraction set. You can always exchange any subset of your abstraction set with a count variable. So it's a general theorem given that you have an abstraction set.
Okay.
And then that's kind of the next question. How do we compute these abstraction sets? In theory, we would like to identify subsets of blocking variables that are exchangeable in the sense that I already showed you, especially when we're using sums as the definition. In practice, exchangeability is very hard to define or to compute. So what we do is we sort of during search, we maintain a graph containing the blocking variables as nodes. And whenever we find a core, a normal core that contains some blocking variables, we update the graph with edges and set the weight of each edge to correspond to how many times we've seen those two variables in the core together. This is sort of a heuristic way of getting. The intuition here is that we would like to abstract blocking variables that are related to each other. And in this work, we say that two blocking variables are related if they appear in cores together. So if we find that the cores that we have don't drive up our lower bound, so the hitting sets that we find from Cplex are not having an increasing cost, lower bound space, then we cluster the graph at some point. And we take the clusters in that graph. So here's that this is independent from the from the instance that we're solving. So we can form these abstraction sets over any instance. It doesn't have to be this pathological worst case. In fact, we only say that and if we have weights, we require that the abstraction sets are only contain variables with the same weight. So the only restriction here is that we only add edges between two nodes that correspond to blocking variables that have the same weight. So in the end, we're going to end up with clusters where every single element in the cluster has the same weight. And this is what we take as abstraction sets. And now let's see the same example. This is the last time, I promise, but this time with the abstractions, abstract cores and abstraction core reasoning. The difference from before is that we also now initialize a collection of abstraction sets. And we loop as before while our bounds are different. And in the beginning of each loop, we now we check the graph and update our abstraction set if needed. In this example, let's say that we pick B2 and B3 to be an abstraction set. And then we add definitions. The abstraction set has two elements, so we need to add the definition for the two counting variables into our set instance, set solver, by using any of the well-known CNF encodings of these cardinality constraints. And the second difference is then in the IP solver. Now we have to sort of extend it to be able to reason over these counting variables and abstract cores. And this is fairly simple to do. We had the definition earlier, and it can be expressed as these two linear constraints. The first one says if we have if the count variable is set to true by a solution, then we have to set at least k variables in the set to true as well. And the second one says the other direction of the. If there are k variables set to true here, then we have to set the count variable to true as well. But note that the hitting set still gives you a hitting set in terms of the blocking variables. It reasons with the abstract cores, but it gives you the hitting set in terms of the original blocking variables. So as long as we don't have cores, the hitting set is going to be empty. And now the next step is then core extraction. We don't get an updated lower bound here. And in order to be able to extract abstract cores, we have to sort of prepare assumptions that correspond to the count variables. So this is the second big difference. Earlier, we just had the assumptions be all of the blocking variables that weren't in our hitting set. Now we also have to make sure that they respect the abstraction set. So for every abstraction set, we check how many variables from that set are not in our hitting set. So we start with all blocking variables except for the hitting set, and then we check how many of a certain abstraction set are in the hitting set, and then we add the count variable that says that we're only allowed to falsify. The intuition here, the better way to saying this is that the count variable in our assumption should correspond to how many are in the hitting set. So we're only allowing the SAT solver to falsify as many variables that are in the hitting set from the abstraction set. But we're not, in contrast to earlier, we're not saying you have to falsify exactly these. Instead, we're saying you have to falsify this many of them. They don't have to be the same. So in this case, in the empty hitting set, we don't have any variables from our abstraction set. So we add this as an assumption, and since we're calling it as a negation. So this variable is defined to be true if there's at least one from the abstraction set to true. So its negation is going to be there are none. And then the core extraction in itself, given these assumptions, the core extraction runs exactly as before. Just notice that now we have the definitions of this abstraction. In order to be for the variables to make sense for the SAT solver, we need the definitions here. So now we get the first core we might get contains only this count variable. We're asking it to find the SAT solver to find a model where none of the variables, 0 of the variables in our abstraction set are set to true. And this is not possible because of this clause. So the SAT solver can detect this and give us back the abstract core containing only this count variable here. And exactly as before, we've removed the assumption from the set that we consider and call the SAT solver again.
So your new cores can contain both original variables and these counting variables?
Yes.
Mm-hmm.
In the simple case, they don't, but in actual examples, they can. We get a model because we don't have any more cores, which gives us an upper bound. The bounds are not the same, and now we go back to computing. This time, maybe the hitting set computation is going to be more interesting. So now, the only core that we have says at least one of the blocking variables in this abstraction set needs to be set to true. So the definition here enforces that. But the hitting set that we get is still going to be given in terms of the original blocking variables. So we can get this. And now we get
also the IPs, but how do you communicate the cores to the IP solver somehow knows that in order to satisfy SAB1, it has to pick some of the...
Yeah, it's here. You add this to the IP solver as linear constraints.
Ah, okay.
So both the IP solver and the SAT solver need to be extended with the definitions. Mm-hmm. So in the SAT solver, we encode them as CNF, and in IP, this is straightforward to express as linear constraints. So now, this time around, when we set up our assumptions, we see that the hitting set that we have contains one variable from our abstraction set. So hence, the assumptions contain the count variable that says, whose negation says, you're allowed to falsify, set one of the variables to true, but not both. So earlier we would have had the negation of B1 as an assumption. So we're saying you can falsify B2, but you cannot falsify B1. Now we're saying you can falsify either B1 or B2, or set the blocking variable to true, but we're not sort of asking, we're not enforcing strictly which one. And this is where the expressivity comes in. So now, here's then an example of a core that contains, we cannot both set only one variable from here to true and set both B1 and B4 to true. Not all of these things can happen at once. We cannot have only one variable from B2 and B3 set to 1, and also both B1 and B4 set to 0. So this is what this core is saying. Then we again get a model, we get a new core. And as I should have maybe said the first time around, in this example, here we could change our abstraction sets, but in this simple example, I won't. But here in this point, at this point, we could alter if needed. And now we go last time to the IP solver and find a heading set that contains 2 elements. And then we're done, because now our bounds match. And now I'm nearing the end of this.
Can I just ask 2 questions?
Sure.
So one question is, when you're basically, I mean, these counting variables are reifying cardinality constraints, right? So in principle, everything you did so far, I could also reify general 0-1 integer linear inequalities. I don't need to insist that all coefficients are the same.
Yeah, this is a very good question, and I think I couldn't review it for obvious reasons, but I think Fahim has a paper at SAT about this improvement this year.
Okay.
So the motivation for having the same coefficients is just the lower bound. You get a well-defined weight for each. But yeah, sure. Sorry, go.
No, that's a good. I mean, I guess you can still get a lower bound in terms of. I mean, you know, for every. Yeah, you'd have to figure out the cheapest way of satisfying this linear inequality, and then that would be your lower bound. Yeah,
in theory, it can be done, and I'm the first to admit that this is maybe the sort of the most obvious thing that we could have also tried, that we didn't for this work. But as said, I think this year's SAT will have an improvement on this.
Okay, and the second thing I'm trying to understand is, like, suppose I run a core guided solver, and I run it with this OLL method, which, if I understand correctly, is sort of introducing these variables that you're looking for. So if I just run a core guided OLL solver but change the assumptions to match what your implicit hitting set solver would be doing, would I get the same, or is there any difference?
That's an interesting question, and it's very close. This is sort of the theory part here, and it's sort of where I don't have a good answer. In my mind, it's sort of about where you want to do the computation. In OLL, you're sort of asking the SAT solver to extract it. Here, you're also sort of letting the IP solver reason over this. But there are similarities, and it sort of simulates. This is sort of the answer of why these abstract cores can drop the number of cores required by an order of magnitude, because OLL only needs a polynomial number of cores because of these variables, because these variables are more expressive. So,
but basically, just to be clear, what I have in mind, like, I want you to compute all these OLL variables, but your assumptions will still be over only old variables.
Yeah, in a certain sense, yes.
And then you'll use this fact that your OLL variables would have to be two-way, sort of some kind of equivalences, but you'll make your assumptions as if you were in an IHS solver.
I think that would be very close to being the same, sort of off the top of my head.
Okay.
But yeah, I wonder how you would do with weight. how would you like make? No, maybe it will work. You would somehow
yeah.
In a SAT solver, if you do OLL with only a SAT solver, you need to be sort of do this clause cloning and like residual weight things to make sure that you're not over relaxing the formula.
Yeah, so this residual and cloning and stuff, this I never understood, but that's because we never need to, like if you're in a native pseudo Boolean setting, you don't need to worry about that.
Well, the idea is that you want to, if you're doing SAT or MaxSat, you want to avoid encoding the pseudo Boolean constraints. You want to stick with cardinality constraints.
Yeah, no, yes, I understand.
It's a good point. Yeah, it's at least very close, and I'm sure whatever minor differences could maybe be fixed fairly easily. And we sort of touched upon this, and this is sort of the question. For an unweighted MaxSat instance, we could form an abstraction set that contains all of your blocking variables. And then we could show that then it's guaranteed that you'll terminate within a polynomial number of cores, because at most you need to extract a single core for each sort of cost. A core saying you need to falsify at least 1, at least 2, at least 3, at least 4 up to your cost. So you're never going to get to exponentiality here. But in practice, if you do that, then your CNF encodings of the definition constraints are going to be very large. So here's the sort of trade-off between the larger your abstraction set is, the more expressive it is, and the more compact cores you can get. But on the other hand, you have to encode your definitions, and those encodings can get very large, and that might end up hurting the solvers more. So there's a balance here. And then on the other hand, if your abstraction sets are too small, then you won't end up winning anything. Then they're not expressive enough to capture a large number of cores. So the solution we proposed in this paper was this graph-based heuristic, which turned out to perform fairly well, but I'm sure there's more that could be done here, and more sophisticated ways of computing the sets.
And actually, that would also be a difference from OLL plus core guided, because there, I guess, our only abstraction sets would be cores.
Yeah, true. Yeah.
Whereas you are somehow, you're not restricting yourself to cores. You can somehow identify other interesting sets.
That's a very good point that I should have thought of myself. But that's absolutely true. Yes, we don't have to do cores as the abstraction sets.
Can I ask a quick question about this, please?
Sure.
So I'm just trying to understand, in the example you described before, if instead of all sets of size R, say sets of size n/2, you take some random half of them.
Yeah. So
then the cardinality, then at least in my, and yeah, in this example, so it's not all sets of size R, but some random half of them.
Mm-hmm.
Then somehow cardinality is not the right mechanism, at least in my mind. Like it's not, it doesn't capture this.
So where do you mean that we have half of them, in the sets of cores or in the constraints?
In the hard clauses, instead of
okay,
all sets of size R, just then the theoretical statement you made at the end, I just don't see how to. So does it make sense? Or
I mean, I said that there exists sort of the theoretical statement is not that on every, it's weaker. We're just saying that there exists MaxSat instances on which we need an exponential number of cores. So this is an example of such a MaxSat instance. But you're right. If we have fewer constraints here, then we probably won't need as many cores, I would think, at least sort of off the top of my head. If we only limit this to have, we'll probably not need as many cores, I think. I hope.
The problem is how you would encode the hard constraints in that case. I mean, the beauty with this cardinality constraint is the encoding will be very concise, and that's why things get exponential. Like if I just pick a bunch of random sets, then the CNF might become very large.
Yeah, it depends. Now we're measuring against the n is the number of blocking variables, but that's true if you want to say half of these sizes are forbidden. I don't think you can do that. There might be some better way, but I can't immediately think of another way than sort of enumerating all of them and saying not this, not this, not this, not this, or not this. And then that's going to be an exponential number of hard clauses.
So potentially, if this may be an example where the abstract framework is not as effective.
Well, I mean, the next part I was going to was sort of, this is the sort of motivation why we started looking into this. But then of course the experiments that we ran were on these general benchmarks. So for the most part, we probably won't, I don't think we actually got this sort of drop to a guaranteed drop to a polynomial number of cores. But in practice, I'm sort of a more practically oriented. In practice, it was faster.
If I can hook up to this discussion, I mean, this is very easy statement that always a polynomial number of cores is sufficient. Because as your abstract set, you just choose your objective variables or like your soft variables.
Yes,
and then what you do now is you have one variable saying like for every possible value of your optimization problem.
Yes, this is
one variable that says like, oh, we need at least one soft clause, and one variable saying at least two soft clauses, and so on.
Yes, this is not.
What you're doing is you can always kind of like just try out what the solution is, and in SAT will at some point say unsat, which means there is no solution with this few soft clauses, and then for one more it will say sat, and therefore you know where the solution lies.
So this theorem actually uses that you're unweighted in that sense then?
Yes.
Yes. And this is exactly sort of what and I'm definitely not saying that this is sort of a deep and complicated theorem to prove.
But like if you wanted to provoke like a theory, I don't know, a theory benchmarks that might or might not be mildly interesting. Like suppose that you have two n variables. Okay, and then you write down a CNF formula saying that, and you pair them together. So B1, B2, B3, B4, B5, B6. And then you now write down the CNF formula saying that in at least R pairs, one of the variables is true. That should also be a small CNF. And abstract cores, somehow you should still have a lot of symmetry. And the question is, are these abstract cores now still helping you? It's a more challenging setup, but abstract cores should still help in theory. But do they in practice?
That's a good question. That could definitely be investigated more. And especially if you then wanted to sort of change the definition from being, now we're doing sums, but you could in theory do something else as well. Yeah, but that was exactly, and as I said, I'm not saying that this is a complicated theorem, but it sort of gives you the intuition of what's happening. And actually the way, the thing you described with checking for every objective value is exactly what these model improving solvers do. So in a certain sense, you could say that the abstract cores framework can simulate these model improving MaxSat solvers. And then by picking the way in which you abstract, if you restrict to abstracting only cores, you could then simulate core-guided solvers. So there's sort of lots of room here to further exploration.
That was my feeling also, that somehow you're having a framework where you can sort of interpolate in between these three different approaches that you talked about.
Yeah, exactly.
And the question is, does that make sense? It seems potentially like it's fairly intriguing that. And
there are sort of, you could approach that, this does it make sense question, both from a theoretical perspective, like for example with those instances you talked about, or then from a more practical setting and seeing where do you solve things fastest.
Yeah. And I guess I would argue that at the end of the day, the practical impact is the more interesting in the sense that, well, we know that these problems are NP hard, right? So
yeah, sort of, yes. I'm definitely not trying to go for any kind of P versus NP questions here. I'm just interested in solving things, even if they're NP hard. And this is sort of what we already saw. This is just saying that this also works on weighted, even when we restrict to abstracting only sets that have the same weight. We go from this yellow line to the blue line, and the black line is done, I'll say, just like, and then informally, the black line is gotten by when you build these CNF encodings of the counting, you can then try what sort of exhausting the totalizer. So you just try to force the lower bound of these cardinality encodings up by just assuming the single output from this cardinal variable. And this turns out to be very effective. RC2 does this as well. And then sort of to further motivate, these are the benchmark different domains where the basic MaxHS, the green one, and RC2, the orange one, exhibited different performances. So what sort of is the takeaway message here is that the blue one is always, well, not always, but almost always comparable to the better one of these two. So we're sort of introducing ideas from core-guided solvers into the implicit hitting set solvers without taking away the part that the implicit hitting set solvers are good at. Yeah, so of course, if there are questions, we should continue talking, but just to sum up.
I've got a small question before you wrap up. So did you check what if there is overhead on the hitting set solver, or what percentage is where on the in the algorithm? I mean, of the computation. So does it more? It's even more on the hitting set solver, or is it?
We didn't do sort of proper like formal tests on this, but like intuitively, it's a bit more on the hitting set solver because now you have to add more constraints to it. So, but the challenge is to add some more overhead, but not too much.
Yeah.
But no, we didn't test this like to the full extent yet.
And how was it before? Was it like a lot on the? Did you have like 90% of the time were you doing the hitting set solving, or?
Not if you want to do. If you would do this like the first approach that I showed, one core, one hitting set, one core, then you would have something like 80-90%. But since you want to do lots of cores and then hitting sets every now and then, like hand wavily of the around 60-70 on the hitting set.
Okay.
Depending on the instance. If you can of course construct instances where core extraction is really hard and hitting set computation is really easy.
Mm-hmm. All right, thanks.
Well, I also have a question, like on the instances where this does pay off, do you happen to know if there actually are cardinality constraints in these instances, like at most one constraints?
No, I wouldn't know. They do appear. I mean, it's a fairly common constraint when you're doing sort of application domains. In many applications, you want to say.
Are you? May I try to interpret your question, Stefan, as asking whether this is like a rewriting technique? That you have a CNF encoding on something that should be written in another way, and this is recovering the way it should have been written, or?
I mean, okay, for sure, if there are, I would hope that the technique of doing this captures that, but it can also capture more than that.
I have a follow-up here. So if it would be just a rewriting technique, that would be quite easy to test, no? because we could just add all of these cardinality constraints in advance, not use the abstract course, and just see what the improvement is like between using the abstract course or just adding the new variables,
Yeah, I mean, that's true. And the computation of abstraction set, it's heuristic in nature, so it's not guaranteed to be complete, but at least in these extreme cases, it should capture most of those at least some of the cardinality constraints. But that's an interesting idea to test for sure.
It's more of the kind of insight into solving experiments that maybe somehow you don't do them too often, right? Because they don't pay off in the next competition, but they would give scientific insight somehow. I don't know, but do you know this fact that you can choose abstracts, that you don't have to do your abstraction sets over course, that you could pick any set that you like? Do you have any idea whether these sets typically actually are cores or whether they would be unrelated to cores?
Well, I mean, in the approach that we use here, they're sort of maybe unions of cores in a certain sense, because the clusters will only include variables that have appeared in cores together. So you might have like 3 variables, A, B, C, where B and C have appeared in a core together, and A and B have appeared in a core together, and then that might be clustered. So in this setting, I would say they correspond to like many cores, but if you do something else, they wouldn't have to. But then on the other hand, picking which ones you want to abstract is not an easy question.
No, but it's like, I mean, again, you could, if you take just I guess I'm just thinking like one way you could take this and just dump the IHS style assumptions on an OLL based solver, and then you would get your abstract sets only over cores. Or you could take like this OLL based solver and but change the abstract sets so that when you do the rewriting, you would like add these abstract sets instead and see what happens. Again, it's sort of this, you can interpolate in between the two.
For sure.
I just have a quick question. So I missed the first part of the discussion. I was just curious, did you discuss the connection like between abstract cores and pseudo-Boolean solving?
Because what do you mean, pseudo-Boolean solving?
Because I was just wondering if there was any discussion on that, because abstract cores, from what I understand, they would capture that it's essentially talking like about the sum of variables has to be greater than some value.
Yeah, I mean, we talked. Yeah, I mean, for core guided solving, sure. But how do you mean pseudo-Boolean?
But in pseudo-Boolean, this is so essentially core. So I'm brainstorming, so please feel to. So I'm brainstorming, so it's not a well thought through thing. But essentially, it's that in abstract cores, what they do, they hide this problem of resolution of reasoning over cardinality constraints. And then in pseudo-Boolean solving, well, this can be written as a linear inequality, and it's a bit more, let's say, native to the solver itself.
For sure.
Yeah, so I was just wondering whether this is one way where we're trying to actually just fight the problem that, for example, stat solvers don't have cardinality reasoning. But if they would have, maybe would it still be useful for abstract?
That's a good point. So if I just may sort of, I don't know if this is what you're asking, Amir, but let me take inspiration from your question and maybe remake it completely. But like one observation is that I think if you're running if you're running the conflict-driven framework not on a CNF translation of your problem, but on 0-1 linear inequalities, then one thing that can happen, and that sometimes does happen, not too often, but it does happen, like your core, quote unquote, could actually be a cardinality constraint. So in that sense, like if you want to say that at least, out of these 5 variables, at least 3 are true, that could actually be a core. That could be something that the black box, the SAT engine returns to you.
For sure. I mean, I would assume that if you have a very effective sort of pseudo-Boolean reasoner, then it could be that the abstract course, this kind of framework wouldn't pay off.
I mean, I think I think this is also related to this re-encoding question, right? Like, because if you actually have the cardinality constraint and it's just badly encoded, then you could actually get this cardinality constraint as kind of your core back, and then it wouldn't pay off, I think. But the nice thing about these abstract scores is somehow that you add them, even you have like no clue if there actually is a cardinality constraint over these variables. As you're just reifying them, and you just say like, well, and go figure, right? Like, I mean, you just then like assume that there's one, and then the solver figures out if it actually is or not.
Yeah.
While the cores would need to be actually implied, so they would just reformulate your instance.
Yeah, I mean, when you're trying to sort of, as I sort of said, trying to just solve things efficiently, there's always this. This is a sort of automatic technique that's independent of the domain. But if you have more domain-specific info and you're solving a specific problem, then usually my intuition would say that it pays off to use that. So if you know you have cardinality constraints in your problem and you want to solve a specific problem, then I would recommend use those. But if you don't know or are solving someone else's problem, then there are some automatic things that you can try, such as this.
But I'm not sure. I mean, it's even like, I would not be surprised. Like, I would definitely, I mean, so time is a finite resource, but if I had like infinite amount of time, then this is one of the next things I would try to implement, I think, because we've seen in other settings, like one intriguing, I think what you're saying, Stefan, is this is kind of, again, like you're recovering a good encoding from a bad encoding. Okay. And one other way of doing that, this is a AAAI paper last year, I think, that we had, was this cardinality detection, where you run a pseudo Boolean solver. We know that they're not good on CNF formulas, because if you write the cardinality constraint in CNF, then a pseudo Boolean solver like cannot decode. Like inherently, the algorithm is unable to do that. So then what we did, we added an algorithm that on the fly sort of searches for hidden cardinality constraints. Okay, and of course, then you take like the crafted benchmarks, which are CNFs that hide cardinality constraints, and sure enough, this technique is amazing. Okay, so no surprises there, otherwise it would be failed. But one thing that was quite surprising to us was, now you take a cardinality, like you take a hard pseudo Boolean instance. The encoding is, there's nothing wrong with the encoding. It's encoded in exactly the right way, but it's just a hard instance. Okay, and then somehow the pseudo Boolean solver goes wrong, and it should learn like all these nice cardinality constraints, but it doesn't. It learns clauses instead because, I don't know, the heuristics are not good. And then it turned out that this rewriting technique was actually helpful, because it somehow said, oh, well, this is my very fluffy interpretation, but it somehow said, okay, now you learned all these tons of different clauses, but let me help you to see that if your conflict analysis had been better, you would have probably have wanted to learn this cardinality constraint instead. So let me help you. And it's like quite conceivable that these abstract sets would somehow gently, you know, nudge even a pseudo Boolean solver like in the right direction. Like, did you consider this cardinality constraint instead? Maybe. Maybe, yeah. So I think I would view them like the pseudo Boolean question or the abstract core question, in some sense, probably complementary. I don't know. Yeah, I mean, yeah, you're right. I mean, I don't know either. It could be that it doesn't pay off. It could be that it's amazing. But this could be that it helps somewhere and doesn't on other instances.
But this AAA work that Jakob mentioned now, somehow I feel like it's a very similar, not a similar idea, but it's somehow very connected to these abstract cores, because both are recovering kernelity constraints that are hidden inside the instance. Well, I haven't read the paper that Jakob mentioned exactly. Except how it works.
That paper, you cannot speculatively, we can only recover cardinality constraints that we've seen. So we'll never, paper will never like postulate, hey, I'm guessing based on, it's only like, it's actually collecting basically at a very high level what it's doing. It's collecting clauses in the naive clausal encoding of a cardinality constraint. And then when it like sees enough of them, it will say, actually, I've seen X1 or X2, I've seen X1 or X3, I've seen X1 or X4, I've seen X2 or X3. Maybe, I'm starting to suspect now that maybe all of variables X1 to X4 except one have to be true. Let me check. And that check is kind of triggered automatically on the fly, but it won't trigger unless you've actually seen a lot of these binary clauses.
Yeah, sure.
So here,
Yeah,
this
okay,
is
so
more
that's the
like
main
speculative.
difference.
And the information we use doesn't have to be in the formula. This course, they're entailed by the formula, but they don't have to be clauses in the formula. I haven't read the paper you mentioned, so
okay.
Yeah, those clauses also don't have to be in the formula. We discover them in the implication graph.
Okay, then.
But it's still, yeah. Interesting. I guess, did we even allow you to finish? I guess we didn't, maybe.
Well, it's a very basic finish. IHS solvers are nice, and they were nice even before abstract course, and now they're even better. And read the new handbook. There's a new handbook on satisfiability. I think Jakob has written a part about pseudo-Boolean solving, and Matti and Fahim and Ruben wrote about MaxSat. And
abstract core, but abstract score wouldn't be in there, I guess, or would they?
No. It might be a reference, but not described in detail, because this one came out a bit before, or was in press before.
I have a question about these handbooks of sensibility. I was just curious, does anybody know how come they're not open, so like they're not like open access?
I guess most books are not.
Okay, so I guess that settles it then.
Good question.
Well, because for papers and journals, like now we're pushing for open access. At least I've seen like lots of things in that direction. But then there's like the handbook accessibility. The other day I was trying to find it, I found it, and I couldn't access it. So I was like, too bad.
The MaxSat chapter is, I think Matti has it as a preprint. I think there were discussion about the authors having a sort of, the authors have the rights to give out their chapters, but the whole book, I haven't seen either.
Okay.
But also the author, I mean, I actually asked for an author copy to post, and then they give you a PDF of the true published version, but it has a watermark that says author's copy or something. So it's a bit annoying to. I think the best bet is to, like, if you know the title of a chapter, you Google it, and chances are you'll find the latest version before copy editing by the publisher, I guess. But yeah. Okay, other questions?
Maybe one more remark. Jeremias, somewhere in the beginning of your talk, you said one of the nice things about these implicit hitting set solvers is they always call the subcalls on the same instance. You broke it.
I broke it, yes.
You broke it, yeah. Then,
it's this sort of, but I didn't break it as much as core guided solvers break it. So you want to break it a bit, but not too much.
all right.
But yeah, I mean, the point, I guess that one of the nice things is that the invariant that still holds true, I guess, is that everything you've ever learned is valid, right?
Yeah.
So, I mean, we're just throwing in new clauses, but anything that followed from your old clauses, any learned constraints should still be good.
Yeah, I mean, and you can still continue. I think summary, and we tried, you could also continue extracting normal cores if you wanted to. You could just decide to extract basic cores, while in an OLL implementation in MaxSat, it might be that a core you found earlier isn't a core anymore after the reformulation steps.
Okay, so if there are no further questions, or maybe even if there are further questions, maybe we should continue them in an offline mode. So one thing that we didn't do so far is, and I'll do now, better late than never. So thank you so much for this wonderful presentation, starting with the very basics and then going